Previously, we extracted all the relevant features that we wanted for our content and style images. The content features are now good to be used as they are, as the convolutional neural network does a good job of extracting content elements from any image that is fed into it. Although we mentioned that the style features require one additional pre-processing step to be more useful. The researchers in the style transfer paper implemented the use of a Gram matrix for more effective style feature extraction. This is an important step, as generally, any features extracted from the convolutional network still hold significant content-related information, such as object structure and positioning. And by applying a Gram matrix to these extracted features, the content information is eliminated. However, the style information is maintained, it's preserved. This is quite a lengthy topic to discuss, as style extraction from images could be an entire course on its own. So feel free to see the second article attached called Texture Synthesis Using Convolutional Neural Networks. I've placed it in the article right before this video if you wish to learn more about this fascinating research. For now, we are going to move forward, keeping in mind that applying a Gram matrix to features extracted from convolutional neural networks helps to create texture information related to the data. Having said this, it becomes important to first discuss what a Gram matrix is, before we can move forward. A Gram matrix is defined using the following simple equation, where V is an arbitrary vector and you multiply it with its own transpose. So Gram matrices are relatively straightforward. So let's implement a function to apply the Gram matrix to our specific situation. So what we'll do is on the bottom cell, we're going to define a function def Gram matrix. And it is simply going to take an image tensor as input. Our tensor currently has 4 dimensions, so we're going to have to reshape our tensor in order to apply the Gram matrix transformation. So let's begin by unwrapping our tensor dimensions into their respective variables, accessing them like so. Now our first value will be the batch size B, the second one the image depth D, image height H, and finally the image width W are the values that are being unpacked from tensor.size. And now that I think about it, we are not going to be using the batch size variable, so we can ignore that. And now let's use our depth, height, and width to reshape our data into a 2-dimensional array, or a 2-dimensional tensor, I should say. So using tensor.view, we can reshape our tensor. We will maintain the depth as the variable d, as this defines the number of feature channels in our tensor, the depth. In order to get a 2-dimensional tensor, we are going to multiply the features of each input channel, the features being the height and width of our tensor, h times w. And now we have a 2-dimensional tensor that has been reshaped to store our tensor data. And now unwrapping this resulting tensor into a new tensor variable means that we are just one step away from applying the Gram transformation to our data. And now that we have a 2-dimensional tensor, as mentioned earlier, we simply have to multiply it with its own transpose to get the Gram matrix. And we do this by defining a Gram variable that we will use to store our Gram matrix. And then we can then use the torch.mm command to multiply 2 matrices together. These 2 matrices being our tensor and tensor.t, which is the transpose of our original tensor. And finally, we can conclude this function by returning our Gram matrix. We now have all the functions we need to actually make the process of style transfer work. The feature extraction function and the Gram matrix function are crucial for making it all happening. So now we can finally implement these functions of ours to get amazing results. In a new cell, we apply the Gram matrix function to the style features that we extracted earlier. So we create a dictionary called stylegrams, and we are going to map each layer to the Gram matrix of its corresponding feature. So the key for our dictionary is going to be the specific layer, while the value is going to contain the Gram matrix of the respective style features for that same layer. All right, now what we can do is iterate through each layer inside of our style features dictionary to make sure that we get the Gram matrix of all the features that we previously extracted. So now we have all of our features extracted, and we also have a dictionary containing the respective Gram matrix of all the features that we extracted. As mentioned earlier, we have chosen 5 layers to extract features from. This provides a variety of avenues for reconstruction of the image style, which also leaves room for customizability. We can choose to prioritize certain layers over other layers by associating certain weight parameters with each layer. Layers close to the beginning of the model are usually more effective at recreating style features, while later layers offer additional variety towards the style elements. So a customized arrangement which weighs the early layers more heavily would be ideal for us. This can once again be done using a Python dictionary element. So let's call this dictionary style weights right onto our next cell. And we seem to have invalid syntax, and that is because I forgot my end statement. Everything else seems to be good. Alright, so let's call this dictionary style weights. And we can run through all of our style layers and place them as dictionary keys. The keys being conv11, conv21, conv31, conv41, and conv51. Simply the 5 layers that we have chosen to extract our features from. Remember, this was only for content extraction. Alright, and now as we said, we will weigh earlier layers more heavily. So for our first layer, we will place a maximum weight value of 1. The second layer will take a weight of 0.75. And finally, the last few layers will take much smaller weights of 0.2 each. 0.2, 0.2, and 0.2. Notice that we did not place our conv4 layer in this dictionary. As I have just said, it is used entirely for content extraction as opposed to style extraction. Alright, and now another weight parameter we need to define is the amount of balance we dictate between the content image and the style image. This allows us to customize our final target image by defining the ratio of style to content. This ratio is referred to in the style transfer paper as alpha beta, where alpha represents the content image weight and beta represents the style image weight. The relevance of this ratio might not seem significant. However, the following images show just how much variance this ratio can have on the final results. And using these two images, the left image for content and the right image for style, the following results were obtained for varying alpha-beta ratios. The respective ratios can be seen on top of the images. As you can see, the lower this ratio gets, the more style is implemented into the final target image. We are looking for results that more closely resemble the lowest alpha-beta ratio seen here, namely 10 to the power of -4. Furthermore, we won't be running too many iterations on our target image to speed up the process for you guys, so we will be using an even lower ratio to ensure we get good results and effective style transfer. So in our case, what we're going to do is define the alpha value as content weight and set that equal to 1. Similarly, we define our beta value as style weight and set that equal as 10 to the power of 6, which makes the value of our ratio 1 divided by this 10 to the negative 6. This is the ratio that we will use, as I have gotten very good results with it. But feel free to play around with the weights as you please. I highly recommend maintaining the content weight at a value of 1 and playing around with the style weight instead to adjust your full ratio. Now we are going to use our style and content image data to optimize our target image. The first step in this process is to actually define our target image. While the style transfer paper starts with the target image being a random white noise image and then optimizing it, we are going to start with our original target image being a clone of our content image. The optimization process is then going to try and maintain the content of the image while applying more style from the style image with each iteration of the optimization process. In the context of code, this simply means that our target image can be obtained using the content.clone statement. The content variable referring to our content image, and we want to add an additional method to the statement called requiresGrad. And you've seen this before. And we are going to set this equal to true. And you should have a basic intuition as to why that is, since we want this target image to be adjusted along with our optimization process. Thus, gradients are required. And since this is involved in our optimization process, we must connect this to our GPU using .toDevice. And this concludes the initialization of our target image. Alright, now we finally have all 3 of our images, and we can begin the target image optimization process. We do that in the next lesson.